We are Group 33, and our project is the Motion Detecting Sentry Turret. Our group consists of one electrical engineer, Caitlin Martin, and three computer engineers, Ladurma Gary, Michael McAllister, and myself, Quinton Jimenez. The overlap in our majors has allowed the team to work more seamlessly together on different aspects of the project. The motivation behind our project is multifaceted. Our group wanted to create a piece of technology which could be applied for recreational uses, such as paintball tournaments, as well as security and military purposes, such as the protection of properties and controlled lands. The Motion Detecting Sentry Turret project will be safe for usage and testing by students. However, the technology is expected to be modifiable to suit more dangerous conditions. The key specifications for the Motion Detecting Sentry Turret are outlined in this table. Among the primary specifications, the sentry turret must be accurate to a minimum of 70%, meaning that 70% of shots fired must hit their mark. The turret must be able to traverse or rotate 180 degrees horizontally and 45 degrees vertically. The range of effect for the turret is required to be between 10 and 75 feet from the device itself, within the cone defined by the horizontal traversal specification. The power supply should last 3 hours on a single charge. The minimum ammunition capacity should be 20 rounds, and the maximum weight of the device should be 40 pounds. There are a number of hardware-specific requirements for this project. For computer vision to be used, the sentry turret must have a camera. This camera should have a high enough resolution to determine human figures from between 10 and 75 feet away. The sentry turret will have a warning system to indicate to potential targets that they are in danger. For this purpose, a 55 lumen LED light will shine from a visible position on the device. The ammunition container will be large enough to contain a minimum of 20 rounds. The total weight of the device is not to exceed 40 pounds, as owners of the sentry turret should be able to reposition the device without additional assistance. Given that the position of the device is intended to be easily variable, the sentry turret must have an onboard power supply which can power it for up to 3 hours on a single charge. The members of Group 33 have satisfied these specifications at a cost of $600 or less. The software specifications for this project are as follows. The sentry turret should use computer vision to identify targets within a range of 30 feet. Motion sensors on the turret should trigger an interrupt which activates the camera and computer vision algorithms to check for targets within 30 feet. When a target is located within range, the LED warning light should be activated. The turret must be programmed to cease firing when no target is within the 30-foot range of fire. The software should also perform calculations to continuously track and aim at the target while the target is moving. The block diagram on this slide not only indicates the interactions between the components of the motion detecting sentry turret, but also the distribution of responsibilities among the members of Group 33. Ladurma Gary was primarily responsible for decisions regarding the camera and warning light for the project. Caitlin Martin approved the actions relating to the power supply, PCB, and stepper motors. Michael McAllister was in charge of computer vision and the computer used as an auxiliary computational device. The computer was necessary because the processor on board our PCB is not powerful enough to run computer vision algorithms at a satisfactory speed for the purposes of the sentry turret. Quinton Jimenez was responsible for the servo motor and triggering mechanism for the sentry turret. Finally, the members who worked most closely with the microcontroller were Ladurma Gary and Michael McAllister. The sentry turret functions as follows. First, the power supply provides power to the PCB, which distributes that power to other areas of the device as necessary. Next, the computer receives feedback from the camera, then uses computer vision to process the images. Computer vision algorithms determine information necessary for the microcontroller to position the stepper motors. The PCB activates a warning light when the computer vision system has identified a target, and the microcontroller rotates the servo motor to trigger the paintball marker while the stepper motors track the target.
When choosing our material, we took both cost and sturdiness into account. We explored both wood and metal, and while MDF or pine would have been more cost-effective, it would not have been as sturdy or as weatherproof as we would need. So we settled on steel, as it was cheaper to acquire and get laser cut compared to aluminum. Here is the final structure for our turret. The base changed slightly due to using reclaimed materials to save on budget. We also added a spot to mount the air tank and batteries at the base. On the left, you will also see our electrical box, which houses our PCB and drivers, and mounts to the side of the base.
We originally thought to use a single board computer, like a Raspberry Pi or BeagleBone, for both turret control and computer vision. However, we feared the SBCs within our budget did not have the performance to process the camera's video stream at an acceptable frame rate, which is important for the turret's accuracy. So, instead, we decided to use an Arduino microcontroller for turret control and a laptop for computer vision. After further thought, we decided to take the Atmega MCU from the Arduino Uno and use it on a custom PCB instead. The Atmega 328 is compatible with the Arduino IDE, making it easier to program for, and also has enough I/O pins for our project. The laptop has enough power for computer vision, but does limit the portability and self-sufficiency of the turret. We had several options for our microcontroller and settled on the Atmega 328P, the CPU of the Arduino Uno. It had sufficient performance, I/O pins, affordability, and it was convenient to use. By having an Arduino microcontroller on our PCB, we would be able to use the Arduino IDE to program it, making software development faster and easier. Several group members also already had Arduino Uno boards, which we could use as prototyping boards, saving us money and time.
For our turret warning light, we looked at several options available. A more expensive option would be a unit that would be already programmed with flashing modes versus a standard bright LED. We chose the latter as it would help cut down on costs and have a lower energy consumption. We can then program our LEDs to flash via the MCU on our PCB. Either webcams from Microsoft or Logitech would be chosen as they are compatible with either Raspberry Pi or Arduino. Ultimately, Logitech was chosen as the brand to pick from as they have a wide selection that is compatible with our project, and Logitech's webcams have been reviewed with high performance and reliability. Image processing will play a vital role in our project, so our camera selection would need to include a supported webcam or camera module. For this, we chose a webcam that we can easily move on the turret. Our choice was a Logitech C920S that can be used with either Raspberry Pi or Arduino. It has a resolution of 1080p at 30 frames per second to support our project's image processing.
When determining the types of motor we would use on this project, we ended up choosing to use two stepper motors to control the horizontal and vertical rotations of the gun, and then a servo motor to control the triggering mechanism. We chose to use a servo instead of another stepper motor because the triggering mechanism would not require as much power as what we would need to control the movements of the gun. For our stepper motor drivers, we've updated our selection from previously to the DM542T due to the old carriers being too small for our applications. My initial calculations based on the weight and speed of the steppers wouldn't move at, I assumed the max current would not exceed 2.8 amps as were the previous drivers' max current. The new drivers offer a configurable continuous and max current above what the steppers would ever be able to pull. Also, the drivers found were half off for this from the original price of $55, making them easier to fit into our budget. When choosing our power supply, we knew 24 volts overall would be necessary. The issue with having one 24-volt battery was the high cost. Then we opted to explore putting low voltage batteries in parallel to get the 24 volts necessary. The 12-volt batteries that would be large enough for our project became costly, and the cheaper options wouldn't allow us to run the system for as long as we needed to. So we opted to use 2 leftover 12-volt batteries, which allowed us to save money, but they are slightly bigger than necessary for this project. When selecting our servo, we determined that it would only need to be pushing about 4 kilograms per centimeter at the most to trigger the paintball gun. So we chose the Tower Pro MG995 as it is compact and easily fulfills our requirements. Here is our finalized PCB design. It includes a 24-volt input that leads to a 12-volt regulator, which is used to power our detection light. The 24-volt input is also connected to a 5-volt regulator, which is used to power the Arduino stepper motor drivers, trigger, and USB connection. For the USB connector, we chose an all-in-one wire due to the FT232 chip and all alternatives being out of stock and unobtainable for a fair bit of time. This is the second rendition of our PCB, and the most notable changes made were choosing a larger, more suitable wire terminals and fixing the footprint of the LM2576. The problematic footprint can be seen below, along with an assembled picture of our PCB.
This is our project's functional flowchart. The process starts when computer vision detects a person. It then communicates with the MCU on the PCB, which starts a cascade of events. The stepper motors start moving to track targets, while the warning light turns on to alert targets that they are in firing range. The servo motor will then engage to fire upon targets until they are out of range. The monitoring process will then resume to repeat the process over again.
For an overview of our software, it is split between our laptop and the PCB. The laptop handles the computer vision aspect of the project, while the PCB handles the direct controls over the turret's functions. To the left is the software flowchart, where you can see the program flow and interactions between the laptop and PCB. Both the laptop and PCB are initialized at the same time, and the program only starts after the user calibrates the turret using the laptop. Calibration is done to align the turret to the center of the camera and to ensure the turret's accuracy. The laptop takes a video stream from the camera, processes it with a human detection algorithm. Once a human is detected, a bounding box is drawn around them, from which a centroid is calculated. When there are multiple targets, the distances from the turret's current aiming position to each centroid is calculated, and the centroid closest to the turret is made the target. This prioritizes the closest target to the turret every time. The necessary steps to reach the target are calculated, and the laptop then formulates a command to bring the turret closer to that target in the form of a string of 4 digits. This command contains orders for the turret's two stepper motors, trigger servo, and warning light. Then, this command is sent over a serial connection to the PCB. The PCB promptly decodes this string and acts upon these commands. After doing so, a confirmation message is sent back to the PCB, indicating that the PCB is ready for the next command. This exchange is done to ensure the PCB isn't swamped with old, outdated commands, and this process is continuously repeated until the turret is disabled. The laptop utilizes OpenCV for acquiring and processing the video stream from the camera. OpenCV comes with a pre-trained histogram of oriented gradients, or HOG, and linear support vector machine, or linear SVM, which we use for pedestrian detection. The HOG is specifically used for feature descriptor extraction, and the linear SVM for feature classification. The histogram of oriented gradients goes through every pixel of an image, comparing to each pixel directly surrounding it, checking how much darker the current pixel is compared to the surrounding pixels. The algorithm draws an arrow called a gradient, showing the direction of the image getting darker, repeating this process for every pixel in the image. The image is divided into cells, each of which has a histogram of all gradients within that cell. To account for lighting, these cells are then combined into normalized blocks. The blocks are used as features for the SVM. The SVM is a supervised machine learning model that divides and classifies data. Since our SVM comes pre-trained, we can get right to classifying the features within the images as pedestrians or not. Once classified, if a pedestrian is detected, a bounding box is drawn around them. This bounding box is used to calculate the target's position, which is then used to derive the necessary actions of the turret. The programming language utilized is Python, since it is simple, easy to debug, and familiar to the group. We are using the PySerial library to make serial communication simpler. Instructions are sent to the microcontroller as a string of numbers, where each number corresponds to a specific instruction for the microcontroller. For example, a 1 in the first position would be a command to fire, while a 0 in the same place would be to hold fire. The PCB is built around the Atmega 328 microcontroller, which can be programmed using the Arduino IDE. As mentioned earlier, the PCB receives instructions from the laptop as a binary string, and translates this binary string into commands for the turret's functions. These functions include the pan and tilt stepper motors, the trigger servo, and the warning light. The trigger servo is served by a single digit, indicating the turret to fire or not. The warning system will also have a single digit, on or off. The pan and tilt servos will have a single digit each, with a digit indicating which direction the motor should step in. If time permits, we will experiment with variable speeds and introduce an additional digit for motor speed, or rather, the number of steps taken.
Here is our actual results of the testing. Our accuracy landed at 50% due to overcompensating targeting and lack of frames. Our traversal was a success, and our range was 10 to 30 feet, which landed into our effective shooting range, which was successful. The building process for our project will have 3 phases. Phase 1 will include us developing software for computer vision and code for our motors and lighting for the MCU chip. Phase 2 will commence building the unit and testing the viability of our software and code. Changes will be made to the code and turret as testing moves further along. Phase 3 will be the final touches as we ensure the turret is functioning and ready for demoing. This is a breakdown of responsibilities for each group member. For the tasks that require more work, we will assign a primary and secondary person, denoted by P and S respectively. Liderma will be primarily on the warning light. The mounting and casing will be handled primarily by Caitlin, with Liderma as secondary. The camera selection will be primarily handled by Liderma. Computer vision coding will have Michael as its primary. Power system and PCB design will be assigned to Caitlin primarily. Arduino coding will be handled by Michael primarily and Lerma as secondary. Validation and check-in will be done by Quinton primarily, and the servo mechanism will be primarily done by Liderma with Quinton as its secondary. This was Group 33 with the motion detecting sentry turret. We hope you enjoyed our final presentation. Thank you for listening and have a great day.